Hello, everyone. Today is day 10. We're getting close to the 12th day of NeurIPS, and today we're going to talk about vision. Just as a disclaimer, vision is not our primary focus here at Relational AI, but we deal with it, and there are some areas that they're very important for us. But in the spirit of finding out what's going on in vision, it's always good to have a look, even if it's not your primary area of focus. So this is the best paper award. It's called Visual Autoregressive Modeling Scalable Image Generation via Next Scale Prediction. And I feel like I need to mention, because this is part of the best paper, the main author was an internet by dance, and there's a lawsuit against him. So it's kind of interesting. So you can see the GitHub repo where you can find the implementation. And vision has always been a little bit challenging on the generative part. Although, in the beginning we had GANs, the GANs worked remarkably well. And at that point, we didn't really have a great generative model for text. Then we had the variational autoencoders, the flow-based models. You can tell there's kind of like a pattern. There's, sort of like all of them look like there's an encoder-decoder architecture, and the diffusion model, it's kind of like the same. There's an encoding process, if you want, going that way, and then a decoding process. I don't know if we should call it decoding or encoding, but there's a bidirect. There's two directions. One of distilling information, and the other is like of generating. And this is kind of like the idea of the autoregressive models, what you know as GPTs, the encoder architecture, encoder, decoder, the language model, the transformer architecture, as you know it. And, so far we've been very familiar with that, but just in case anyone attends this talk without knowing much about language models, there is a tokenization process, and there is different types of tokenization, kind of like sometimes subwords or even like character level. There is a compression, language model compression in semantic space, and there's a loss function. Usually we are, trying to predict the next token, and sometimes this is also called a maximum likelihood and cross-entropy loss with teacher forcing. Details, we don't really have to delve into them now. So the image tokenizer and autoregressive transformers, they have some challenges. First of all, practically they perform significantly worse than state-of-the-art diffusion models in high resolution image. I think they believe to say synthesis here. There's a typo. Autoregressive models have not demonstrated the same scaling law properties as LLM in text generation. So something is not going well over there. And due to raster order prediction, autoregressive models suffer from very slow prediction speeds. The raster order scan is not the most natural order for images, as it loses the global information for crucial, which is crucial for visual modeling. So it's kind of like scanning linearly the image is not the way that you process it. Of course, people can say that producing text in a linear form is not the most natural way that people think, but I think here it's more important because you lose context, which is very important, and it can be further ahead. There are even some more. So for those of you who don't know, the AR transformer or the IGPT, the VQ GAN, all of them, they're trying to predict the next block. Okay. And let's see some weaknesses of this image tokenization: mathematical premise violation, the VQ vector quantized, I think that's what it means, variational encoded token with interdependent feature vectors contradicts the unidirectional dependency assumption of autoregressive models, inability to perform some zero-shot generalization. The unidirectionality nature of image autoregressive model restricts the generalizability in tasks requiring bidirectional reasoning. Structural degradation, the flattening disrupts the spatial locality. So the fact that you basically unfold everything in one line is a problem. And something that I hadn't thought about, but if you put the math down, although transformer in text is, n square, I think becomes n to the sixth when it comes to images. Not very practical. So these challenges lead us to ask the following questions. Can autoregressive models generate images of comparable or even higher quality than diffusion models? Is that possible, or we have to give up? Can autoregressive models in visual generation exhibit the same scaling law? Okay. Remember, the whole conference was all about scaling laws. We saw, I think, in our previous talk, how important it is to be able to build predictors for, what's your loss function or what's your precision is going to be in the next scale. Other than if you don't have that, you can't do pre-training. So, exhibit the same scaling properties as LLMs, where the generation quality improves with scaling up the model size and compute. And at last, can autoregressive models, while retaining the scaling law properties of LLM, adopt a more suitable order for image generation instead of raster scan order? So, and this is the birth of the visual autoregressive transformer, and not by next token, but by next scale. Okay, it's kind of interesting because if we remember some of the technologies that brought a revolution, let's say in image compression, like back in the signal processing days, it was wavelets, was like the multi-scale approach. They were quite successful. And even, if we go to more practical stuff, when you download an image from the web, you download it progressively at different scales. Okay, so first you see something that is blurry, it becomes the precision and the accuracy becomes better over time. Of course, now with 1 gigabit internet, you don't really see that much, but that's how it works. And kaboom, that's really the thing over here. LLMs use an autoregressive approach to predict the next token as language has sequential order. However, this method is not suitable for visual data due to unique characteristics. Traditional image autoregressive models use a sequence that is not intuitive to humans, but is suitable for the computer processing. Sometimes that's not a bad idea to do, but sometimes it doesn't work. This sequence predicts image tokens only but by one by one in a top to bottom or row by row raster approach. So the visual autoregressive modeling is a new generation paradigm that redefines the autoregressive learning on image as coarse to fine next scale prediction. And in summary, here are the highlights of the paper. You see a lovely example. Which, by the way, this is how diffusion is working. Okay, so we kind of like put diffusion to the transformer here. It's a new visual generative framework using multi-scale autoregressive paradigm with next scale prediction, offering new insight. We discussed that. An empirical validation of our model scaling laws and zero-shot generalization potential, which is initially emulates the appealing properties of large language models. And it's a breakthrough in visual autoregressive model performance, making GPT-style autoregressive methods surpass strong diffusion models in image synthesis for the first time. So that's something to keep in mind. And it's always nice when you use the same architecture. Who knows how this is going to help in better multimodal models. We'll see. It's definitely, I think it was a breakthrough worth the best paper award. Now we're going to go back to OpenSora, which is an expo. We mentioned that before. This is from a company called HPC-AI, which started as a colossal project, I believe, from Berkeley. And so this is a company that it's more like an infrastructure, as a service for deep learning. But by trying to demonstrate its use, they offered this interesting application, which you can download, train on your own premise, or you can use HPC-AI as your infrastructure provider to do it. So text-to-image model weights, large-scale video pre-training, high video data fine-tuning. So this is kind of like the direction, the pipeline. So yes, and you see here the 3 phases. And the training process, they used a variational autoencoder. For video, they also use the text encoder for text. I believe the STDIT here stands for diffusion transformer. I don't remember what the ST must be text. So in a sense, is you're encoding video and text, and then you're decoding video. Okay. Yes, with text embedding in the latent space, and they list the parameters 700 million, 100 million, and the text encoder 4.7 billion. Yes, Labis, you have a question?
Yes, Nico, quick question. Yes, so could you give a sense of the cost of training these models? Do they?
I think they have it. I don't know if I have it in my presentation, but I remember I've seen it in their presentation. So if you go and watch the full video, it should be there. But it was surprisingly something affordable. So the nice thing is that I think it's fully open source. They give you everything, and you should be able to replicate, but you should also be able to use it. So if you have interest, you should look at it. It's not that expensive as you would expect. So here's the model architecture. They used a T5 model. T5 is a die-hard model. It's a bit so T5 surprisingly is the only model that I know that follows the encoder-decoder architecture in language models. People have moved to decoder only, the GPT, but it's still being used. And this is kind of like the way that they train their diffusion transformer here. So they encode the video, they code the prompt, and they do the training. So they do have the efficiency. I don't know if it's cost here. It's not cost. They're based on the PixArt model, which is I think it's from Huawei. So in general, the SPC.ai has there's a lot focused around China. They have a lot of big collaboration there, and I think they're based there. And they claim some speed ups. You can read more about the paper and efficiencies. Again, it's not an area of my expertise. They do offer pre-configured images. So they have customizable environments, pre-configured images for you to use. So the Colossal AI, I think, as I said, the Colossal AI is the framework that they're using, I think, which is coming from Berkeley, if I remember correctly. They have models. They have, reasoning models. And of course, they have the OpenSora. So large models. You can get them from there. So I think here they're advertising more their company. And they also give you some credits if you want to use it for research. They have a lot of interesting, offerings, and they claim that they're quite competitive when it comes to GPUs like H100, H1200. It's paid by subscription, paid by week, paid by month, on demand. Looks like, I say here is that comparable to Ranford, possibly, but I think they are a competitor to Ranford, in my opinion, and they seem to offer more models. Yes, so I haven't seen the price, but you could potentially, I think they mentioned in the paper about how many hours they were using, but the models are not very big. At least, they have a small model. They train over 20,000 videos. The videos are usually a few minutes. They're small. And they give you the big one, the one which is 1.1 billion plus another 348 million for the images. And that's like a training data of 30 million videos. It's decent. And here they mentioned some challenges they had about high number of small files, which is a problem, data scale, high bandwidth and low latency, multi-cloud and multi-cluster training scenarios. There's a lot of MLOps, DevOps, whatever you call it, work that you need to do on the, you need to work around. And here's kind of like they also had to expand into storage because they have terabytes to petabytes of videos, segments ranging from a few megabytes to tens of megabytes. I think they're talking more about the problem and probably actually, now that I think about, with 30 million videos, these numbers are easy to reach, especially if you think you need to decompress. Yeah, also every time you have a checkpoint, you must be able to save it very quickly. And again, here how they brag about their business, the best paper. I think they became known from helping Google to reduce the BERT training time from 3 days to 76 minutes. I think that was a colossal project. Anyway, in my opinion, now we're getting into the kind of like interesting part. It's interesting. It's an interesting story. We all know, and everybody expected. It didn't come as a surprise that GANs, along with, of course, the sequence to sequence, made it to the test of time award. Thousands of references, several variations. The main author, Ian Goodfellow, he couldn't be there. He was he had to join through Zoom, and that's because unfortunately he suffers from long COVID. And the reason why I mention is because he talked about that and what a big problem it is. For those of you who know him personally, he is a very athletic person, very active. He got some mild COVID in summer, and he couldn't expect that this would convert to long COVID. And he said, he wanted people to be aware, and he's being active about research in that domain. Because apparently a lot of people from our community, or some people from our community have been hit by that. So I feel like, we need to mention that it's part of the conference. So if we need to set the stage, we are back in 2014, 2 years on from the ImageNet moment where, Hinton showed that deep learning can actually do something useful in images. And that was, a defining moment for the deep learning community. So pre-AlexNet, people were doing unsupervised layer-wise pre-training. We don't know what happened to that. Nobody was ever able to explain why this worked and then it didn't work, or it wasn't as. And of course, I wasn't as influential or as important as we thought. And then feature learning was the, the state of the art. Then post AlexNet, it's all about what supervised deep networks could do. So it was everything supervised. So this is the evening of May 26, 2014, Montreal, Quebec. 12 days to NeurIPS deadline. And some students went to this bar and they started having a conversation. And that's where, we and Goodfellow start this idea of, a discriminator and a generator. For those who don't know, he had done his internship at Google about adversarial neural networks. I think it was before the GAN. So he had some kind of like seen something over there. So it didn't, I don't think it fell from the sky, but I'm not sure. I think so. Maybe he went after to Google for that. I don't know. Anyway, so he goes, he codes that, and then what happened is in 12 days they wrote the paper, and then some people graduated and some people left for internship. Behind the scenes, there's always something that makes things happen. And what got it done? Intellectual environment at LISA. This is the predecessor of Mila. So for those who don't know, LISA, maybe, I think that was the first AI symbolic software back in the 80s, probably. The spirit of collegiality that led to the outing in the first place. So it's good to go out and discuss and not stay in the lab. That's something we know really well at Relational AI by doing cons and meeting in person. Why? And Zan Pouget Abadi, an intern, had a background in game theory that no one local had. So you always need an outsider to come and, plant the seed. And of course, let's not forget that Ian wouldn't have been able to code it overnight if Theano didn't exist. And, I just feel like I have to say that because everybody knows Torts and TensorFlow. But the beginning started with Theano, was a performance differential GPU accelerated tensor programming in Python. That was the first attempt to create a specialized framework for deep learning. And it was flexible enough to accommodate unconventional research ideas like GANs. Okay, so let's not forget the software behind it. And here, after the submission, authors go separate ways. Ian departed for Google. I think that's where they wrote the paper about adversarial machine learning. So maybe the GAN paper was ahead of time. Mehdi Mirza, Simon Sindero explored conditional case on archive in November. So people worked on the conditional GAN. And Ian publishes on this distinguishability criteria for estimating generative models, making connections to noise contrastive estimation, or like a theory paper. The authors feel like it deserved more attention. And before we go to the evolution, I just want to say that the paper laid very low on the conference, didn't really get that much attention. It didn't become it didn't get a spot for an oral presentation. But then it kind of exploded. People started looking at it, and we know the rest is history. And this is the evolution from 2014 to 2020. You see the quality of the images becomes better and better. And this is now. I didn't know, but 2023 there is still papers on that. And it's still the fastest game in town. The GigaGAN, 4K resolution, text conditional samples, samples in 3.60 seconds on last year's hardware. So which is pretty fast. The legacy of GANs. One of the methods that showcase incredible mileage from large-scale training, data-driven perceptual loss with conceptually simple tools from supervised deep learning. The field started taking generative models for synthesis seriously. I can vouch for that. And tackling unsupervised learning with supervised learning machinery, also true. So well-deserved. And these are the orgs that provided the funding. So thank you also to the agencies that made that possible. We saw that in a different talk, but this is the in painting in the diffusion era, and it's really amazing how you can just go and you can sketch something and it can give you what you want. So here you in paint, you create a rocket and you give it a I should have put sketching and not in painting. Although I think with the same technique you can do in painting as well. But I mean, it's really impressive what diffusion models can do these days. And now we're moving to the last talk that it's more like an application of vision backed into the agent models, okay? And how it helps us create world models. So the title of this invited talk of the self-supervised learning theory and practice workshop, it's called Self-Supervised World Modeling from Internet Data. And it is a game changer. We know that in reinforcement learning, we need, a network, a policy network, and we need an environment, which is the world model or the simulator. Typically, when it comes to AlphaGo, it's a system that it's a program that knows how to, verify Go and play the next. But that simulator, that world model, can be built from data from the web. And that's what this talk is about. And to me, it's the new reality and opens. This is what we like calling the digital twin. So it's basically making digital twins from, internet data. And again, this is how the reinforcement learning works. You have action, and then you split it. You try different cases. So you're basically trying to predict you're trying to know something about the future to optimize the current decision. So you say, well, if I do this, what is the state that it's taking me to? And that's how we solved AlphaGo. But I've said that before several times. The reason why the AlphaGo didn't really we didn't see it becoming viral in the enterprise world or in other places was because it was very difficult to build specialized simulators. Okay, so we didn't have a way of, it was difficult to make a simulator, especially something that had to do with things in 3 dimensions. You need a lot of, these are expensive simulators that you have to build with 3D graphics. And, so we can have a perfect simulator, but we can have a world model, which is a learned simulator. This is probably, we should have made that more obvious, but a learned simulator is a world model. And so we talked about the word, what a world model is. You can do it from internet data, okay? And you can do it for embodied agents, which means that they're agents that they live in that environment. And here we're going to see the next steps, what happens after you build that. And here are the references, which I should have extracted, but I haven't. Okay. And the idea over here is, you can ask about doing a task. For example, I want to cook something. And obviously, when you want to cook, you want to not just give the instructions, but demonstrate where the next movement needs to be, like how you're going to achieve your goal. So you say slice a carrot or move the carrot to the board. All these instructions, they have to be there. Now, what is interesting is that we can really make we can make this word model from data that you can find from Common Crawl, from Wikipedia, from Stack Overflow, from GitHub, even from Wolfram Alpha. Wolfram Alpha, you can think about it as a symbolic generator, and the unified representation is basically text over here. Okay, and even for images, you can also convert it to text. And you can also unify tasks with text generation. And I will explain what I mean by that later on. So when it comes to, so this paper over here is, yes, they're both coming from the same paper. Video as the new language for real world decision making. The point we're trying to make over here is that you can basically pre-train your model as a text generation model. But you can also use the video as the universal language as well. So we use the text as a way of building a word model for text-related tasks. And here we can do the same, but using the videos and images, okay? And in this particular case, you give an instruction and you create a video generation that show you how you do the task, and you get basically, so this is kind of like I'm saying what I want to do, and the system does it for me. Okay, so it simulates my actions. You can give a task, cut pepper, and you can see, what it's doing, what it means to cut a pepper. Okay, and you can also instruct, you can have here a robot, and you say move into that direction, and it performs the movement for you exactly by following the dynamics, okay, the physical dynamics. And of course, you can give an instruction for learned egocentric movements, turn 90 degrees, and it does that for you. And if you want to find, you can download the models called Universal Simulator. You can that was done by Google, and basically now you can do reinforcement learning by using this Universal Simulator as your word model. And I think this completes our presentation for today. We have two more. One is dealing with data, and I think that we're going to close with math. So thank you very much. We'll see you tomorrow.